Hi, this is Dr. Khan with Chapter 6.1 and 6.2. We're going to introduce volcanoes, and we're going to start by comparing two different eruptions that give us really two of our main kinds of volcanoes. And we'll see there's more than two, but really these are contrasting two opposite types of volcanoes what it comes down to is their composition, based on their composition of the magma. So stuff that we learned all the way back in minerals and rocks about felsic versus mafic is going to come back into play here. So it's worth looking at that again. And why, again, some volcanic explosions are really devastating and forceful, while others are more like a lava oozing out of a volcano in a way that's much more calm and gives us more time to react. So you'll be comparing and contrasting Mount St. Helens in Washington in 1980. That was the largest historic eruption on record for North America, and an entire cubic kilometer, so a kilometer wide, a kilometer deep, a kilometer tall of material came out as ash and rock debris. There was what's called a pyroclastic flow and mud flows. So almost 60 people died. And in contrast to that, we're going to look at the Kilauea volcano on Hawaii that has been erupting on and off for a while, but it does not have an explosive eruption. It's very fluid lavas that kind of ooze out, and it still can be destructive. These lava flows have destroyed over 180 homes and a national park visitor center. They destroy roads very often. So we'll start looking at our Mount St. Helens picture, and I think the before and after is really drastic. The after looks like some kind of other planet, right? It's kind of devoid of life altogether. All the trees are gone, and the entire top of the mountain, an entire side of the mountain was blown off in that eruption. So what is the difference? When it comes down to it, we're looking at a compositional difference between basaltic, which is mafic, and granitic, which is felsic, magma. So looking at the magma itself, basaltic or mafic magma, remember those are rich in dark silicates. It's low in silica overall compared to granitic or felsic magma that's high in those light silicates. Our light silicates were things like quartz and feldspars. Our dark silicates had magnesium and iron in them. That's where that word mafic comes from. And really, the reason that they have such different chemistries between those two magmas comes down to where they came from. So from basaltic magma, we have a partial melting of the upper mantle. And the mantle is very mafic in nature. Those are more dense materials compared to our granitic crust. That's actually our granitic magma that results from a melting of continental crust. So our crust material, which is already more felsic and granitic to begin with, when it melts, it becomes a magma that's very felsic. This chart is in your book, and it's incredibly important because it really ties everything together in terms of what the composition of the magma has to do with everything else. So first, looking at that composition, we have basaltic, andesitic, and rhyolitic. Remember that from our igneous rocks. Basaltic, again, being our mafic. Andesitic was in the middle, and then our rhyolitic or granitic is our felsic kind. So we remember that our rhyolitic or granitic or felsic magma is the most in terms of silica content, around 70%. Our andesitic, which is our intermediate, is about 60%, and then our basaltic magma has about 50% silica content. But what's new here, what's being introduced here, is also the idea of how much gas the magma contains. So we have the most gas in our felsic magma, and then the trend is downwards as we decrease in silica content. We have less gas. The temperature scheme is also different here. Take a look. Our eruptive temperature is the highest for the basaltic magma, lower for intermediate, and the lowest for our felsic. Viscosity, which is a topic that I want to make sure that you understand what that word is talking about. Viscosity is resistance to flow. So water flows very easily. It would have a low viscosity. It doesn't resist flow. But something like pancake syrup, if we try to get that to flow, that's not going to flow as well as water because it has a higher viscosity than water. It has a higher resistance to flowing than water would. So I want to make sure that that's clear in your mind as you read through here. So viscosity, so basalt is more like water compared to our rhyolitic or granitic felsic magma. This one's going to resist flow. Our rhyolitic or granitic magma is going to resist flow. This one's more like the pancake syrup, or the basaltic is more like water flowing. And then tendency to form pyroclastic. So pyro meaning fire, clastic meaning rock bits. So superheated gas and rock that slides down the mountain. This is incredibly destructive and part of why we see a foreign looking landscape in what was once Mount St. Helens. That hot cloud of gas and ash and dust just racing down the side of the mountain and incinerating, burning up anything in its path, and tumbling down these rocks that are essentially on fire. So not really likely to happen in a basaltic eruption. You know, you have the greatest risk of that with more silica that you're adding in. And the type of volcanic structure, the landform that results, also has to do with that composition of the magma again, because our basaltic magma is more runny. Remember, that's like more like water. We get these broad, large areas that the magma, once it's erupted into lava, the lava will kind of spread out a lot more easily, creating these huge, broad structures called shield volcanoes. And that's actually what Hawaii is. We get composite cones with our intermediate. And with our granitic or rhyolitic, we get pyroclastic flow deposits. We get lava domes as well. So again, if we have explosive eruptions, that's really determined by the viscosity, the resistance to flow. So higher silica means higher viscosity. We're talking about our granitic or rhyolitic magma. Higher viscosities are more explosive. So our felsic magmas make more explosive volcanoes. And then gas content. The gas is going to play a role in terms of how explosive the eruption is, but it's that same relationship where the higher the amount of silica, the more gas content there's likely to be. When we have something that resists flow, we're going to have trapped gases, and those trapped gases are going to build and build and build up pressure until they force their way through an explosive event out to the surface. I do recommend at this point you pause and watch the Smart Figure video 6.5.